Hello students, welcome to our YouTube channel Experience Tutor. Today we'll discuss class 12 physics, electromagnetic induction, chapter 6, ncert solution, part 3. Before we begin, we have a humble request. Please subscribe, like and share our channel among your friends and relatives. Please click on the subscribe button to support us. So, let us begin today's lesson. Today's lesson will start with question number 6.12 because in the last lesson we have completed 6.11. A square loop of 12 centimeter and its sides parallel to x and y axis is moved from is moved from is moved with a velocity of 8 centimeter per second in a positive x direction in an environment containing magnetic fields and in positive direction. The fields is neither uniform in place nor in space nor in constant in time. It has a gradient of 10 to the power minus 3 Tesla per centimeter, also negative x direction. That is, it increases by 10 to the power minus 3 Tesla per centimeter as one move in the negative x direction, and it is desiring an up at the rate of 10 to the power minus 3 Tesla per second. Determine the direction and magnitude of induced current in the loop if its resistance is 4.5 meter ohm. Let us see the solution. So in step 1, we'll write the summary of the questions and the given values. Side of the square loop S is equal to 12 centimeter, that is 0.12 meter. Area of the square loop, that is A is equal to 0.12 multiplied by 0.12, that is 0.0144 meter square. Velocity of the loop v is equal to 8 centimeter per second, that is 0.08 meter per second. Gradient of the magnetic field along negative x direction. dB upon dx is equal to 10 to the minus 3 Tesla per second per centimeter, which is equal to 10 to the minus 1 Tesla per meter. The rate of decrease of the magnetic field dB by dt is equal to 10 to the power minus 3 Tesla per second. Resistance of the loop R is equal to 4.5 meter ohm, that is 4.5 multiplied by 10 to the minus 3 ohm. Step 2. Find the rate of change of the magnetic flux. Rate of change of magnetic flux due to the motion of the loop in a non-uniform magnetic field is given by d phi by dt, where we can write d phi as a dB by dx multiplied by v. Putting the value of values and upon solving, we get 11.52 multiplied by 10 to the minus 5 Tesla meter square per second square. Therefore, rate of change of flux due to the explicit time variation in field B is given as d phi dash by dt A multiplied by dB by dt, and upon solving we get 1.44 10 to the power minus 5 Tesla meter square per second square. Step 3. Now, since so what we'll find here in step 3, we'll find the value of induced current. Since the rate of change of flux is the induced EMF, the total induced EMF in the loop can be calculated as E is equal to 1.44 multiplied by 10 to the power minus 5 plus 11.52 multiplied by 10 to the power minus 5, which is equal to 2.96 multiplied by 10 to the power minus 5 volt. Now induced current we can write I is equal to E upon R. Putting the value of E and R we get, and upon solving we get 2.88 multiplied by 10 to the power minus 2A. Hence the direction of the induced current in such is such that this is such that there is an increase in flux through the loop along positive z direction. Let us see the next question. Question number 13, 6.13. So it is desired to measure the magnitude of the field between the poles of a powerful loudspeaker magnet. A small flat search coil of area 2 cm square with 25 closely wound turn is positioned normal to the field direction. Then quickly snatch out the field region. Equivalently, one can give it a quick 90-degree turn to bring its plane parallel to the field direction. The total charge flown in the coil is 7.5 microcoulomb. The combination of resistance in the coil and the galvanometer is 50 coulomb. Estimate the field strength of the magnet. You have to find B. B is equal to question mark. Okay, let us see the solution. So step 1 is we write the summary of the question and all the given values. Area of the small flat search coil, that is A is equal to 2 centimeter square, which is equal to 2 into multiply by 10 to the minus 4 meter square. Number of turns on the coil is equal to N is equal to 25. Total charge flowing in the coil Q is equal to 75 point. So total energy flowing in the coil Q is equal to 7.5 microcoulomb, that is 7.5 multiplied by 10 to the power minus 3 coulomb. Total resistance of the coil and galvanometer R is equal to 0.5 ohm. In step 2 we'll find the value of induced EMF. So induced current in the coil I is equal to induced EMF upon R. Induced EMF is given as E is equal to minus N d phi by dt, which is question 2. Hence, so where d phi is the change in flux. So comparing equation 1 and 2, we get I is equal to minus N d phi by dt upon R. I dt is equal to minus N upon R d phi. This is equation number 3. Step 3. Find the field selection. Or find the field strength. Initial flux through the coil phi I is equal to BA, where so where B is equal to magnetic field strength. Final flux through the coil 5F is equal to 0. Integration using 3 on the other hands, we have integration of I dt, and we have again n, n upon r integration phi I to phi f d phi. Now we can write, upon solving we can write q is equal to minus n by r phi f minus phi I, which is equal to minus n by r minus phi I is equal to n phi upon r. So q is equal to nba upon na. Upon solving and upon putting the values and solving, we get 0.75 t. Hence the field symbol remains the same of the magnet is 0.75 t. So now we'll see problem number 6.14. Figure 6.20 means this figure shows a metal rod PQ resting on the smooth rail AB and positioned between the pole So in figure 6.20 shows the metal rod PQ resting on a smooth rail AB and positioned between the poles and permanent magnet. The, the rail of the rod and the magnetic field are in the three mutually perpendicular direction. A galvanometer G connected and the ray through a switch K. The length of the rod is equal to 15 centimeter, B is equal to 0.50 Tesla, resistance of the closed loop connecting the rod is equal to 9 multiplied by 9 ohm. Assume that the field is uniform A. Suppose K is open and suppose that K is open and the rod is moved with a speed of 12 cm per second in the direction shown. Give the polarity and magnitude of the induced EMF. So the next part of the question is there any excess charge built up at the end of the rods when the K is open? What if K is closed? See, with K open and the rod moving uniformly, there no net force on the acceleration. So the next question is, with K open and the rod moving uniformly, there is no net force on the electrons in the rod PQ even though they do experiment, experience magnetic force due to the motion of the rod. Explain. So in this way there are there are 7 questions and we have to answer all the questions. So let us see the solution one by one. So length of the rod, which is given as L is equal to 15 centimeter, that is 0.15 meter. Magnetic field strength B is equal to 0.50 Tesla. Resistance of the closed loop R is equal to 9 m 9 ohm, which is equal to 9 multiplied by 10 to the minus 3 ohm. So for first part of the question is the induced EMF 9 volt. Polarity of the induced EMF is such that the P shows positive. So positive while and Q is negative ends. So speed of the rod V is equal to 12 centimeter per second, which is equal to 0.12 meter per second. Induced EMF is given as E is equal to BVL. Putting the values, we get 9 milliampere. So this is the solution of part A. The polarity of the induced EMF is such that the P shows positive while and Q shows negative ends. So let us see the next problem. So question number B, is there an excess charge built up at the ends of the rod when K is open? What if K is closed? So let us see the solution. B. Yes, when key K is closed, excess charge is maintained by the continuous flow of current. When key K is open, there is excess charge built up at both ends of the rods. When key K is closed, excess both the ends of the rod. When key K is closed, excess charge is maintained by the continuous flow of current. So let us see the next problem. So the next problem is with K open and the tool and the rod moving and uniformly. There is no net force on the electrons of the rod PQ they do even they do experience magnetic force due to the motion of the rod. Explain. Let us see the solution. So magnetic force is cancelled by the electric force setup due to the excess charge of opposite nature in both ends of the rod. There is no net impact on the electrons in rod PQ. What key D क्या ना कौन सा गया C क्या ना So magnetic force is cancelled by the electric force set up due to the excess charge of opposite nature at both ends of the rod. There is no net force on the electron in the rod PQ. The key when key K is open and rod is moving uniformly. This is because magnetic force is cancelled by the electric force set up due to the excess charge of opposite nature in both the ends of the rod. Let us see the next question. So now question number D. What is the retarding force on the rod when K is closed? Let us see the solution. Retarding force on rod F is equal to IBL when I is equal to current flowing through the rod is equal to E upon R, that is putting the values we get F is equal to I is equal to 1 ampere. Then F is equal to, we can write IBL, putting the value of I, B and L, we get 75 into 10 to the minus 3 Newton. Now let us see question number E. How much power is required to keep the rod moving at the same speed, 12 centimeter per second? When K is closed, how much power is required? So how much power is required to open the K when K is open? So speed of the rod V is equal to 12 centimeter per second, that is 0.12 meter per second. Hence power is given as P is equal to FV. Putting the value of F and V, we get 9 milliwatt. When key K is open, no power is expended. Next question is F. How much power is dissipated as heat in a closed circuit? What is the source of this power? Let us see the solution. Power dissipated as heat is equal to I square R. So putting the value of I and R, we get 9 milliwatt. The source of this power is external agent. Let us see the next question. Next question is G. What is the induced EMF in the moving rod if the magnetic field is parallel to the rail instead of being perpendicular? Let us see the solution. In this case, no EMF is induced in the coil because the motion of the rod does not cut across the field lines. Let us move to the next question. So let us see question number 6.15. An air-cooled solenoid with a length of 30 centimeter, area of cross section 25 centimeters square, number of turns 500, carries a current 2.5 ampere. The current in this is suddenly switched off in a brief time of 10 to the power minus 3 second. How much is the average back EMF induced across the ends and open switch in the current? Ignore the variation in magnetic field near the ends of the solenoid. Let us see the solution. So step 1 is write the summary of the poem. Length of the solenoid L is equal to 30 centimeter, that is 0.3 meter. Area of cross section A is equal to 25 centimeter square, that is 25 into 10 to the minus 4 meter square. Number of turns of the solenoid N is equal to 500. current in the solenoid I is equal to 2.5 ampere, and current flows for time t is equal to 10 to the minus 3 seconds. Step 2, find the magnetic field. So let us find the magnetic field. We know that average back EMF is E is equal to d phi by dt, which is equation number 1, where d phi is the change in magnetic flux, that is NAB. This is equation number 2, where B is equal to magnetic strength, and magnetic strength B is equal to mu naught Ni upon L. Hence, mu naught is the permittivity of the free space 4r multiplied by 10 to the minus 7, and tma minus 1 a to the power minus 1. Using the equation 2 and 3, the equation 1 we get. In equation 1 we get. So calculate the back EMF. Step 3, calculate the back EMF, that is E is equal to mu naught n square 1a upon it. Putting all the values we get, putting all the values we get 6.5 volt. Hence the average back EMF induced in the solenoid is 6.5 volt. Let us see the next question. 6.16a. Obtain an expression for the mutual inductance between a long straight wire and a square loop of side A as shown in figure 6.21. B. Now assume the straight wire carries a current of 50 ampere and the loop is moved to the right with a constant velocity v is equal to 10 meter per second. Calculate the induced EMF. We have to calculate the induced EMF at a instant when x is equal to 0.2 meter. Take A is equal to 0.1 meter and assume the loop has a large resistance. Let us see the solution to this problem. So first of all, we have drawn the graph according to the questions and put the values. So first A, take a small element dy, this one, in the loop at a distance y from the long straight wire as shown in the figure. So at a distance y from this long wire, say this long wire is carrying current here in this way. Now magnetic flux associated with the element dy, d phi is equal to b dA, where dA is the area of the element, dy is equal to a into dy, that is length into breadth. So B is the magnetic field at a distance y. Therefore B is equal to mu naught I 2 pi y, where I is the current in the wire. Mu naught is equal to permittivity of free space, which is equal to 4 pi into 10 to the minus 7. D phi is equal to mu naught IA upon 2 pi multiplied by dy by dy by y. Phi is equal to mu naught I alpha by 2 pi integration dy by y. Y tends from x to a plus x. Phi is equal to mu naught I alpha upon 2 pi x integration of x dy by y. Mu naught a mu naught IA upon 2 pi log e y, limit lower limit is a and upper limit is a plus x. So mu naught IA by 2 pi log e a plus x upon x. For mutual inductance, M is equal to the flux of M. For mutual inductance M, the flux is given as phi is equal to Mi. Therefore Mi is equal to mu naught IA upon 2 pi log E A upon x plus 1, and M is equal to mu naught A upon 2 pi log E A upon x plus 1. Now B is equal to EMF induced in the loop. So E is equal to B dash AV, which is equal to mu naught I upon 2 pi x AV. Given I is equal to 50 ampere, x is equal to 0.2 meter, A is equal to 0.1 meter, V is equal to 10 meter per second, and putting all these values we can get the value of E as 5 into 10 to the minus 5 volt. So last question of this exercise is 6.17. A line charge lambda per unit length is logged uniformly on the rim of the wheel of mass m and radius r. The wheel has light non-conducting spokes in free is free to rotate without friction about its axis. The uniform magnetic field extends over the circular region within the rim. It is given by B is equal to minus B naught K, where A is greater than or equal to R and A is smaller than and equal to smaller than capital R. So what is the angular velocity uh, of the wheel after the field is suddenly switched off? Let us see the solution. And this is the figure given here. So let us see the solution. So line charge per unit length lambda is equal to total charge upon length, that is q upon 2 pi r, where r is the distance of the point within the wheel, mass of the wheel is m, radius of the wheel is r, magnetic field B is equal to minus B naught K. So at a distance r, magnetic force is balanced by the centripetal force. BQV is equal to mv square by r, where v is the linear velocity of the wheel, and putting the values we get b 2 pi r lambda is equal to mv by r. Therefore v is equal to 2 pi b lambda r square by m. Angular velocity omega is equal to v by r. Therefore putting the value of v here we get 2 pi b lambda r square by mr. For r is smaller than a or equal to a and a is smaller than capital R, we get omega is equal to 2 pi b lambda a square by mr, and we can write this value as b naught. Therefore b naught is equal to minus b, b is equal to minus b naught k. So this is given in the question. So this is the solution. Actually they are asking for the angular velocity. So angular velocity is this value. And this is the end of this chapter. In the next class we'll continue with the next chapter, next new fresh chapter. Until then, thank you, and please Subscribe, like and share our channel among your friends and relatives. Please click on the subscribe button to support us and also click on the bell icon to get automatic notification whenever a new video is uploaded by us. Thank you for watching our videos and supporting us. Thank you very much.